Good morning, everyone. Welcome to this last day of UGLO Lamination Summer School. My name is Zsolt Geretovszky, and I'm going to be your first speaker today. I'm sure that you have learned quite a lot about lasers and their use in life sciences during the last 4 days. And I'm happy to take this procedure further. And we'll talk about 3D printing technology to you in my presentation. The reason why 3D printing is included in the problem is twofold. First of all, this is a very hot topic nowadays, and especially its application in the field of medicine and healthcare. Secondly, the actual process is roots back several laser-based processes, as you will see. So basically, majority or a big part of 3D printing is actually benefiting from lasers and their interaction with different materials. To kick off, I would like to put the topic and 3D printing into perspective and show you this very simple graph, which was published a few years ago by Waller's Associates, a company who is basically the same age as 3D printing, because this is a research based company who actually also looking very carefully on the market, especially 3D printing market from the very beginning. And what this graph would like to emphasize is that there are certain milestones in the age of mankind where technical advancement is actually very important and make a big leap in the progress of technologies and for the life of everyday people. What they say is that around 1440, when Johannes Gutenberg invented the printing press, this kind of technical advancement took its first step, and since then the invention of and use of electricity, medicine itself, the radio transmission or telephone lines, the first build of automobiles, the rise of the semiconductor industry, and most recently the make and use of internet are such milestones in the year of mankind that has a very big role in our everyday life. What is a good point for 3D printing is that these guys who are following it very carefully believe that 3D printing is actually the area where this technological advances is continuous today. So what is 3D printing and actually additive manufacturing, how nowadays it's more commonly used? We can say that if we have a digital data on a computer and that represents a solid object, an object which has three-dimensional sizes, then we can build such a material by an additive process using the very simple idea is that we have the object, we slice it up. So using a plane, we form layers or blueprints of every single part of the object. And using a particular process, we actually realize this blueprint in a solid or solidifying by a material. And if we are able to join these layers to one another, then we can have a final object at the very end of the process. So why is it called additive? The additive adjective is coming from the fact that traditional manufacturing processes are typically subtractive. So we are basically removing material from a block of metal by milling, machining, carving, shaping, or by any other means. And this removal of material is quite different from the way how additive manufacturing is working when we are building up something layer by layer. In the past, at the very beginning, actually 3D printing was the term used most commonly, but nowadays additive manufacturing is most common. In this presentation today, I'm going to use both interchangeably, so AM or additive manufacturing or 3D printing, we refer to the same thing. Why additive manufacturing is such a big thing nowadays? The first idea was why 3D printing was actually developed was rapid prototyping. Rapid prototyping means that people usually want to make the first model, the first prototype of a product quickly, and they would like to iterate and improve it until a final product is made. And 3D printing was an easy way of doing that. The other benefit, which is general to additive manufacturing processes, that the shape of the object could be basically anything. So very highly complex shapes are so easy to make as simple ones like a cube or a sphere. The next point, which is a unique property of additive manufacturing processes, that basically you are allowed to build every single part uniquely, customized. There are no need for two parts to be identical, and this customization is more or more required nowadays. So these are the general trends, and before we kick into and I will show you some aspects of this process and how it can be applied to medicine and healthcare, let me tell you one more important adjective about 3D printing, and this adjective is disruptive. If you haven't heard this word before, this is something like revolutionary, even more advanced than revolutionary. So when something has a very good way of making it, and you actually propose a completely new way to make the very same thing, then we usually talk about disruptive technology. And 3D printing is a key example of disruptive technology. So if you look at this picture, traditional way of making a product is starts with an idea that need to be designed. The first prototype or several prototypes are made. The manufacturing starts. You need to assemble the product, distribute, store it, sell it to customers, and finally it ends up at the customer, in their homes, in a factory, and so on. So why 3D printing is so revolutionary in this process? Because basically you can use a printer directly on your desk nowadays and print the product for yourself. So instead of these several steps, you can jump from the very beginning to the very end and print out the object in one step. 3D printing actually not only revolutionizes manufacturing processes. I used to say that 3D printing is able to revolutionize anything what it comes into the play with. So for example, IP or intellectual property things need to be dealt with completely differently if you imagine that instead of a physical spare part, you are selling the digital blueprint, the actual file of the product, to the customer. So instead of ordering a spare part, nowadays it's common to print using the blueprint of the material, the product itself. You may say that this sounds futuristic, and it is, but if I point a recent report to you, the United States Parcel Service actually ordered a report a few years ago because they realize that most of the parcels they deliver are actually contain spare parts for your dryer, washing machine, television, and so on. And they realize that what if they turn their actually post offices into 3D printing hubs? They install the printer, and when you place an order, they will actually divert your order to the nearest hub, which is able to print out the part for yourself. And then the next day, you just go there and pick it up. It's still not existing, this system, but the United States Parcel Service is actually considering of building it in the near future. So what's my aim for today? I would like to show you how additive technologies are actually working and show you some examples how medicine and healthcare may benefit from the disruptive way it actually makes objects. One good reason I found in a recent market report, which was published a month ago roughly, which says that shortage of a skilled workforce due to limited specialized training in additive manufacturing is and will be the bottleneck for the coming years. The lack of such a workforce would restrain the overall adoption of 3D printing in the medical industry. It means that we need to speed up, we need to teach as many students as possible to 3D printing in order not to hinder the progress of the field. So how my presentation is arranged. First, I will briefly tell you about the history of 3D printing. Then I will show you the major steps required to realize an object by 3D printing. A brief summary will be given on how we may classify 3D printing processes. Then I will show you the 5 most important 3D printing technologies. Each technology will be covered by 4 steps. First, I will explain the peculiarities of the technology. Then I will tell you what material can it be used to make. A brief one-page summary will show you the key players, manufacturers who make those machines. And I will summarize by showing the pros and cons of each technology. Last but not least, we'll follow the medical application and a brief outlook. So let's jump in. So although 3D printing is a big hype nowadays, you can read about it everywhere, but the technology itself is more than 40 years old. It was the 1980s when the first 3D printing technologies has been developed, proposed, and patented. You can see a few key steps, and down below 3 pioneers of additive manufacturing technologies. The first guy on the left is Chuck Hull, who in the States actually proposed stereolithography processes for making a quick prototype. Actually, he was the one who received the first patent for his proposal, and actually he is the founder of one of the first and the biggest 3D printing manufacturer, which is called 3D Systems Incorporated in the States. So he's actually really started a very successful line of study, and later on a very successful business. Still within this decade, there were 2 other key steps for additive manufacturing. The first one, or the second one, is actually devoted to Carl Deckard, this gentleman here, who was a PhD student at Texas University when he proposed to use a powder instead of a polymer or resin for the same fast prototyping need. The process, what he actually invented, now we call selective laser sintering, or SLS, and even today this is one of the key processes I will also talk about. You immediately realize here that I painted laser red on this slide just to remind you that this is a process which heavily relies on the use of lasers for 3D printing. Last but not least, this British gentleman on the right, Scott Crump, was the third one who, a year later, patented fused deposition modeling, which is the most widespread and cheapest technology for building 3D object. I will also talk about this later on. The second decade, which is important, was actually centered about the foundation of key companies who are developing technologies and producing machines for 3D printing. And in parallel, there was a need and urgent requirement towards software development. And this is the area where personal computers were already around, but not as common as today. Most of the time in this decade, these computers were not able to draw something. They were only able to type text on their screen. So imagine how important it was to develop the so-called CAD, computer-aided design, the ideas and the programs, the so-called CAD tools that assists the actual printer in realizing the design itself. The key companies are marked there. The third decade, starting around the millennia, was actually about gaining widespread visibility. So these were the years when the first results became mature enough and actually appeared in the news, in television, and so on. What kind of results were they? For example, in 2002, the first 3D printed kidney was made by Wake Forest University for Regenerative Medicine. So medical applications were still present from the very beginning. Another interesting development these years were the development of the first color 3D printer. You will see later on that what is more common and much easier is to build a monochrome object with 3D printing, but there are certain cases when color is a must. For example, the retail industry always requires very fancy and colorful prints. How it went further, the first prosthetic leg was also made in 2008, and Organovo, an American-based company formed by a Hungarian gentleman, attempted to make the first blood vessels with 3D printing technology. Last but not least, our current decade, or actually the previous one, was flooded by results and development. I just want to point you to two medical-related results. The first one is this synthetic jaw, which was made in the Netherlands, and this is the first one which a patient is benefited for. And the other thing is this small image in the middle. In 2019, an Israeli lab at Tel Aviv University made the first 3D printed heart with this technology. Okay, so what the process looks like step by step. The first point I must stress is that 3D printing is not a single push of a button process. As you will see in the coming minutes, actually the process is much more complex and requires 4 different preparation steps and 3 post-processing steps along the way. These 8 steps altogether are not required by every single technology, but this is the most general description. So let's go through them one by one. First, we need to generate a digital object. There are basically two ways of doing that nowadays. The first one is starting from scratch. So basically you sit down by your computer, use a CAD program, and draw what you need. This is the easiest way in some sense, but sometimes it is not enough. Imagine you have a broken piece you need to amend. In that case, you would like to know how the remaining part looks exactly. For that, you need to transform a real object into the digital space, and this is what is called 3D scanning. And this scanning is another way of generating digital data. When you have the data, you need to prepare it for 3D printing. This preparation basically means that you need to slice it up. So after a spatial object is generated, you need to prepare the slices. During this slicing, an important step also occurs, and this is what can be seen on this graph. The actual CAD file is indicated by these red circles, but this is not the data that the printer will receive, but instead we try to cover this area, this ring, with small triangles which cover the area the most. It depends on the resolution, what you are aiming for, and so on. The idea is that you need to convert the CAD file into layers of this so-called STL file. This is the standard triangle language or standard tessellation language, what it is used for. And depending on the number of slices and the resolution you used, the fidelity of your 3D printing product will be quite different. Obviously, if you have a rough approximation, you can build it faster. If you have a nicer, higher resolution process, then you need more time for it. When you have done with that, you are still not ready with the computer, because you need a few more steps on the STL file manipulation. You need to arrange it over your building platform. You need to select its orientation, because sometimes you need extra structure called supporting structure to build. Most of the time you would like to print more than one part. So if it's a duplicate, you need to arrange those. You need to label them most of the time for storing purposes, and so on. Let me just pick one important part, and this is support structure, what is need to be generated in this step. On this slide, you see two identical pieces printed by two different processes. Don't bother about the actual processes. We will study them later. The polymer powder bed fusion process does not require any extra structure, even over these areas which are actually hanging in the air. And the reason for that is that the polymer powder underneath it will actually hold up the piece during the production. But this is not always the truth. Most of the time, the technology requires extra pieces to build, and these are called supports. Obviously, they are needed for build, but not needed for the use. So later on, we'll come back to this and see that we will need to remove the support structure after printing. Okay, so what else we need to do before printing? Well, because we have a printer, we need to get it prepared for printing. We need to fill it up with the precursor material. We need to do certain alignments. We need to get it ready in many ways for receiving the files. This part of the process is usually manually intensive, not too much automated processes. Most of the development in the last 5-7 years was actually focused on this step of the process in order to transform a laboratory or desktop-based machine into real production lines. Some companies nowadays are ready to fully automate the process because they have invented a lot into this step. Then comes the actual build, when the computer actually sending these layers one after the other and solidifying the blueprint or solidifying the material on the layer according to the blueprint along the layer, and actually also fixing the layer underneath the previous one. And then a new layer is formed, typically by lowering the platform we are building the material on. When everything is done, so the computer and the printer finished, typically after several hours, we need to remove the pieces from the machine, from the platform. We usually need to clean it up. And as I already mentioned, we need to post-process it. One step you already know is that we need to remove the supports if those needed to be built. Another point which need to be done, typically also manually, then you need to polish the surface. It is called finishing, because normally the layer-by-layer nature results in a step-like surface. Even if the layers are very thin, these structures usually there, and these structure may disturb the actual application of the process. There are several ways of removing these structure. One of them is chemical smoothing, when you use some reagent material to flatten the surface. Mechanical abrasion, for example, sandpapering, is another option. Or you can be very clever and paint it. So application of a surface coating is also a way of doing it. But other post-processing steps may also be necessary depending on the technology. For example, when you are printing metal object, you cannot go ahead without heat treatment of the printed object in order to relieve the mechanical stress built up during the process. And last but not least, you are ready to use the product for your application, but you must keep in mind that the product may not be entirely identical in properties to what you are used to by traditional technologies. One way that they differ is that an isotropy, and this means that properties may depend on direction. So the mechanical strength of a fused deposition modeling built structure is usually weaker in the built direction, than the other two directions. So joining the layers one the other is weaker than connecting the materials laterally. Another way of difference is that you don't have a bulk in 3D printing. Therefore, there may be some voids or microstructural differences within the part itself, so the macroscopic behavior will be different than those made by traditional manufacturing technologies. Okay, so these were the 8 steps. Some of them will be visible in the technology part as well. So, but before we go there, a few words about classification. 3D printing technologies can be classified according to technology class, which is basically the price point and intended use of the technology. In this way, there are 4 different major categories. Do-it-yourself category, which is the cheapest one. The personal category is the first level of commercial systems. Basically, these are desktop printers. The technology will show its best if you buy a printer at the professional level. So basically, these machines require a researcher and proper surroundings to run and benefit the most. And the last part, or the last type, is the production grade 3D printer, which are appearing nowadays more and more, typically very highly automated machines, but machines which may not even offer qualities at the professional level, but it can do it automatically. The quality usually of a production type 3D printer is usually in between the professional and desktop level. Another important categorization will be about the processes that actually be used for building up the material, forming the layers, and forming a solid structure. According to this, these are the 5 major categories, which basically physical and chemical means of converting the precursor material into a solid material. What could be these? First of them is called consolidation or fusing, which is a general term using or describing sintering and melting. So if you have a powder and you melt the powder locally, after cooling, the resolidified material will be a solid block. Sintering is a similar process, but does not require melting. This is why we call it solid state consolidation. So basically, you promote the growth of the powder grains to one another, and this can be done at elevated temperature. This is originally a metallurgical process, so you can form a solid structure from a powder by this means as well. The next category in the alphabetical order is an extrusion-based processes, where you actually melt a thermoplastic material, and when it solidifies, then it will form a track and the structure you need. Jetting is something very similar to inkjet printing. So you form very small droplet of the material, which is a liquid. And then when the liquid or some component, the solvent component of the liquid evaporates, then you will have a solid object. Lamination was also a possible technology. It is very simple. You can cut out a piece of from a piece of paper, and if you have a stack of papers with the blueprints, then you can stick together the layers and you have a 3D object. This is something which has been studied in the past, but by today this technology is obsolete. No one is making printers on this technology. And last but not least, photocuring, which is also called wet photopolymerization, is using a resin, a mix of monomers or oligomers, which can be transformed into a solid polymeric material, and which was actually a process invented by Chuck Hull. So basically, wet photopolymerization is the very first technology an AM process can rely on. So let's start with that one. Wet is actually a container, this gray image there, which have a liquid precursor material. This is what is called a resin, a radiation curable resin. Curing is the process in which we solidify the precursors by joining the monomers into a bigger macromolecule, which is basically a polymer. Therefore, we actually solidify the material at certain places. The way how we may assist this curing process could be very different. It could either be use gamma rays, X-rays, electron beams, light, electromagnetic light, and especially UV light. And one of the most common use of lasers are actually in this UV range. So most of these VP printers actually use a laser beam to shine on the surface of the resin and solidify the material. Let me show you, if I can, this short video, which will show you how stereolithography is used by 3D systems. Layers are formed, and in the printer, here is the platform, here's the vat, and where the laser solidifies the material, the platform is actually lowered layer by layer and form a solid object within the vat. When all layers are exposed, your object is ready, so you can remove it from the tank and can use it. In reality, it looks like this. This is the resin. It's a very viscous material. These are the supports. These are the useful parts. And this is how it looks during the process itself. The blue light is shown there where the laser actually hits the liquid surface. Okay, so this is how VP or stereolithography or SLA is actually working. These are all synonyms of the same process. What material can it be used to build? The first point is that it's gonna be a resin all the time, a photocurable resin. So the category of the material is always there, and it doesn't depend on what material properties the final product will show. For example, this one is very flexible, but this is not a flexible polymer, for example, polyvinyl chloride, but a resin which has a property tuned for 3D printing. This is almost completely transparent, but it's still not a polycarbonate plastic, what is used to make bottles, for example, the traditional way, but again a resin which has a very nice and clear or transparent behavior. This is why these likes are emphasized here. So although these precursor materials are sold as polycarbonate, they are really polycarbonate-like, or polypropylene, but they are actually a resin which has very similar properties to a polypropylene. Why is it important? Because the resin nature actually will result in very different behaviors as well. Most of the resins, for example, cannot be glued, while the actual polymers, what we use nowadays and made by traditional technologies, can be glued. So 3D printed products are not exactly the same. They have unique properties. They deliver those properties, but they cannot be considered exactly the same as traditionally manufactured processes. So who are the major vendors of this vat photopolymerization process? First of all, 3D Systems, the very first company, the biggest company who actually invented the process itself. As you can see, nowadays they have plenty of technologies on their portfolio. Beyond stereolithography, selective laser sintering, color jet printing, fused deposition modeling, multi-jet printing, direct metal printing are all there and even growing. And Vision Tech is a company who is well known in the AM field by its proposal of a new way of photo exposure, and this is called digital light manufacturing, or DLM. This means that instead of scanning a laser beam over the surface according to the blueprint, the layer under the growth, they are exposing the entire laser with one shot, because they are projecting a mask instead of a scan laser beam. So everything on the layer will solidify in parallel within the same instant. This was a very good and very promising progress, which helped to increase the printing speed, and which actually was developed further by Carbon 3D, a very new company formed 8 years ago, because they added an extra step in their so-called clip process. This is the continuous liquid interface production. We are still photopolymerizing the material, sorry. But they are forming a dead zone between the platform and the material, and this dead zone will speed the process further, so they are 25 to 100 times faster than any competing technology within the VP field. So what are the benefits and the drawbacks of VP? First and foremost, part accuracy is superior. So the smallest details that can be 3D printed with a commercial printer are coming from this class. Very high resolution, which means 10 micron typically, very good surface finishing are the result of these knowledge. The other peculiarity is a vast size range, which means that we can build very small and even huge structures with this process. Flexibility is another issue. You can use different energy sources, laser, lamps, LEDs, according to the price range you would like to dedicate your processes. And this flexibility is also expressed in terms of material properties, what can be nowadays realized with this process. However, the disadvantage is that we are always using a resin, a mixture which is very special and may exhibit very unique properties. Another general weakness is the mechanical property. They are not too strong. They are improving, but still lack the strength other AM technologies can provide. And last but not least, the products may change the property with time after printing, which is called aging. So let's look at the second alternative, which is called powder bed fusion. Powder bed fusion is a 3D printing process in which we convert a thin layer of powder into solid by consolidation. The machine itself has a build chamber, a powder chamber, and a collector. And the process actually goes like spreading a thin layer of powder over the platform, irradiating it by a laser, solidifying it, then lower the platform and cover the gap by a second layer of powder, repeat the process. So basically, you are building the material inside the powder bed, which can also be seen on this video, which shows you one of the most recent development in this field. A printer which actually uses 4 independent laser beams for building a metal object. This is a production grade machine which actually dices up the print volume into 4 squares and build the material layer by layer in each segment, basically increasing the build speed 4 times as a result of the use of multiple lasers. As I told you, production machines usually do not overcome professional grade machines, but they can do it a very productive way, so to say. Okay, so let's go further and show you just the 4 most important consolidation processes that can be used for solidification. 3 of them, three of them are actually used sintering: solid state sintering, chemical sintering, liquid phase sintering, and the last one is called full melting, when you actually melt the material before the solidification. One unique thing here with the PBF processes is that the powder could be very different. It could either be metal, a polymer, and even ceramics to some extent. So this is going to be one of the major advances or advantages of this technology. From polymers, you can always use several normally used real polymers, which need to be meltable, so to say. For example, polyamides, elastomers, or the newest ones are PEEK or polystyrene. These type of plastics, what can be melted, are called thermoplastic. So by increasing the energy, the temperature of the specimen, you actually transform the metal into or a solid material into a molten material. Composites are a mixture of at least 2 materials. So for example, if you mix glass beads into matrix, into metal matrix or polymer matrix, you are using very unique property combinations, and that can also be generated by this technology. Last but not least, PBF is the key technology for making metallic objects, several of which has already been developed. Commercial vendors. The biggest player is EOS, Germany. They are leading the field in many ways, and they are selling more than 50% of the machines on the market. However, new companies are coming. One of them is Trumpf from Germany as well, which has a very good laser material processing knowledge. But SLM solutions, concept lasers are also big names, so to say, in the field. What can be advantages or disadvantages with PBF? First of all, I need to stress that plastic PBF and metallic PBF is very much different. The powder, for example, is able to hold the solidified material when it is made from plastic. However, if it's made from metal, the molten material will sink into a metal powder. So what I will say now is mainly referred to plastic PBF, which means that you can stack many objects over one another in the build platform if you are building something from a plastic. It is called stacking, and this can also work laterally. So basically, you do not need any support in any direction, because the plastic powder bed will actually hold the pieces in place. And this is how you can make such a nested object, so one object inside the other, because after printing, the extra powder actually can be poured off from the structure. Waste reduction is another key benefit, because unused powder can be reused in very high amount. But the disadvantages are mainly the following 2. Accuracy and surface finish is worse than, for example, VP technologies, and the printing process is not really fast, so usually it takes 8-10 hours to build a 10-centimeter object, for example. The next category is material jetting, and material jetting is a complex process. Actually, inkjet printing was something forming the basics. So you dispense liquid droplets in one way or the other, and when the droplets dries and leave some residue, this residue is used to build the material. There are two major categories of these liquid technologies. One of them is called continuous streaming, when you have a liquid jet, and this will break up into droplets if the conditions are proper, while the other technology is called drop on demand. So basically you have a valve which is able to produce one droplet at a time. Both can be used for 3D printing, but nowadays the DoD is a more common process. The process itself can be easily scaled up. So instead of one nozzle, you can make a line or many lines of nozzles. Nowadays, thousands of nozzles are actually situated inside a 3D printer, and the droplets are actually covering wide areas, something like 30 centimeters at one instant. The reason why you see two different containers here, because one of them is containing the support material, while the other is the built material for allowing complex structures to make. Regarding materials, we don't need to say too much about them, because they are the same resin than used for VP processes, although researchers demonstrated other materials, but they never entered the market yet. Commercial vendors are Solidscape, who made the first machine, Stratasys, who actually joined the field very early, and 3D Systems again employs this technology as well, and one of the biggest players, because they have a proprietary phase changing process which limits the resolution of the print to 30 micrometers. What are the process benefits and drawbacks? It is a low cost process, much lower than the other two already mentioned. It's very nicely scalable, so by putting more valves into the machine, you can increase productivity and resolution to some extent. A unique property is that you can have many materials inside the chamber. Actually, the largest number of materials is 8, which has been demonstrated by Stratasys, and you can print a combination of these materials in one run, and this is something very unique to material jetting, and this is how actually coloring is also achieved. Basically we mix 3 different colors the normal additive way and realize colored images. Disadvantages, same like VP, only the photopolymers are viable, and the material jetting is roughly 3 times larger or longer in resolution than any other thing. An alternative is binder jetting, which has been invented by a student, a university student in the States, when they said that what if we combine powder bed fusion and material jetting and actually jet the glue onto the powder. So the jet itself does not need to bring all the material, it will be provided by the powder. So that was the very simple idea. So basically they made it, and nowadays many different powders can be used in a powder bed and can be glued by special glues dispensed over the surface. Key vendors, I just would like to mention one of them. X1 is a company who is able to build room-sized object with this binder jetting technology. The others are key companies as well. The benefits are basically coming from the combination of two technologies. So they preserve everything good from powder bed fusion, and they overcome the limitation of multiple material jetting because they can be faster, enables to increase the material combinations possible with material jetting, and capable of building bigger volumes. And a con here is the lower accuracy and the worst surface finish among other technologies. You can even feel it with your finger if something is printed by this powder way. Last but not least, fused deposition modeling is the technology I would like to show you. This has been developed by Stratasys and Decker originally. And here, the precursor material is actually a plastic wire, usually a few millimeters in diameter, fed into a so-called hot end, where we melt it, squeeze out from a valve. This is how a hot end looks. And when it leaves the nozzle, it is deposited on a surface. Oops, I think I cannot jump into this video. Okay, I need to leave out the first 44 seconds, and that's too much now. We are very short in time, unfortunately. So I'm sorry about this. The material we can use this technology to build from is thermoplastics, which melts, plastics which can be melted. And there are many different materials available, and many different colors and many different properties can be realized. Even aviation grade material, which are fire resistant, so very hard and not flammable material can be built and made with this technology. The key vendors are Stratasys, as I mentioned, but new companies are always coming, and the reason for that is that the basic and most important benefit of this technology is its cheapness. By volume, this is the cheapest technology, and cheapest means really cheap, an order of magnitude cheaper than any other AM technology I already explained to you. No aging is another advantage, and this is a process which can even be run in an office. So it does not require suction, for example, or good ventilation. It works, it's safe, it's easy. However, there are limitations. One material property or family is the key. Compromised resolution, which means typically a fraction of a millimeter in thickness. The best one was 27 micron, but that's not available in every machine. Because of the bead formed, you cannot make sharp edges and corners on your sample, and productivity is also very limited, as I also already mentioned anisotropic mechanical properties. Okay, so this is just a summary. And I cannot pass this field without mentioning bioprinting, which is not a unique new family of 3D printing technologies, but actually this is a combination of printing and the introduction of living materials, like, for example, cells, growth factors, biomolecules, and so on. The basic idea is that if you are able to make a structure, which is called a support, or scaffold sometimes, and at certain places within the support, you are actually spreading cells and you are able to feed them properly, then they will form a living structure by themselves after a few weeks feeding, basically. So This is surprisingly simple, but very difficult and very complex to control. But still, there are several progress in the field, and I will show some of them in the last part, which will focus on the medical application of these 3D printing technologies. One of them is patient-specific implants, so which are designed to the specific anatomy of a person. Another one are instruments which can assist a surgeon during the operation. It can be dentistry, it can be traumatology. In the next lecture we will hear about such applications a lot. Another area where 3D printing achieved great advances, that orthopedic and making prosthesis either unique or personalized, they are like hearing aids. And two more fields are assisting the intervention procedure, so basically building structures for practicing the medical procedure beforehand, before the operation, or helping to teach future doctors on 3D visualized models. And this is the example I already mentioned in history, that bioprinting can also do a lot. Unfortunately, I need to jump to the very end and leave out a few slides about motivation, basically most recent results in the field. And thank you for your attention, and hope that I can show you that medical 3D printing is really a bright field to learn and study. Thank you. By the way, since I've used up most of the discussion time, I would just add one comment, that during the discussion starting at 11 o'clock, I would be happy to refer to your questions, either asked during the lecture or will be asked during the discussion. I'm going to be around, and thank you very much.